Hello, welcome back to Ali Khan Maths. In this video I'm going to be going through everything you need to know for GCSE differentiation. This includes what differentiation is, how to find the derivative of basic functions, and some example problems involving tangents and derivatives. Differentiation is finding the rate at which the y-coordinate of a function changes while the x-coordinate of the function is changing. In other words, it's finding the rate at which the gradient of a function changes, and it's a fundamental part of calculus, which is the study of change in maths. But first we have to step back a little and make sure that we know how to find the gradient of more simpler functions, such as a simple straight line. So like I mentioned earlier, the gradient means the change in y, the symbol delta meaning change in, divided by the change in x. Because this is a straight line, the ratio between the change in y and the change in x will stay constant throughout, so it doesn't really matter which points we choose. So for example, we'll choose these 2 points over here. So we'll measure down this segment, which is equal to the change in y, along with this segment, which is the change in x. And we can see that this goes from 2 to 4, so it's 2 units. This goes from 0 to 1, so that's 1 unit. So putting that into our formula for the gradient, we have that the change in y is equal to 2, divided by the change in x, which is just 1, and this is equal to 2. So that means the gradient of this function is 2. You can pick any 2 points that are along this line, do the same thing, and you'll get the same answer. Notice that when we were working out the change in y and the change in x over here, we used the coordinates of 2 separate points. So we'll let those coordinates be x1, y1, and x2, y2. These are general and they can be applied to any pair of coordinates on this axis. So working out the change in y is really working out the difference between y2 and y1. So we can write this top part as y2 minus y1. And this change in x is equal to the difference between x2 and x1. So this is equal to x2 minus x1. If you compare this to the points we used the points 0, 2, and 1, 4. So I'll use this as our first pair and this is our second pair. So plugging this into the formula, we get 4 minus 2 is equal to 1 minus 0. And this is just equal to 2 over 1, which is 2, like we worked out over here. Now these 2 formulas we worked out aren't really different formulas in any respect. They're kind of the same thing, because working out the difference between y2 and y1 is really the change in y, and likewise for the difference in x. And this is what defines a gradient, the rate of change between 2 points. Now that was nice and all, but now we're faced with a curve, the graph of f of x equals x squared. What if we wanted to find the gradient of this function? Now you should notice that because this is a curve, the gradient is always changing. The gradient here looks like this, but if we take the gradient at this point, it's much steeper. So we can't ever really find the gradient of the function in itself, but we have to look at the gradient at particular points of the function. So we'd consider the gradient at this point, or really any point on this function, and that's what we'd be asked. But now think about that for a second. The gradient at a point. According to the definition we have over here, the gradient is the rate of change between y and x using 2 different points. So how would we find the gradient at one point? When we want to find the gradient of this line, we use 2 separate points and measure the change between them. But here, if we wanted to find the gradient at one point, that's kind of counterintuitive saying it like that, because the gradient is in itself the change between 2 separate points. So instead what we do is we draw our own lines at the point which we want to find the gradient at. So instead of trying to find the gradient at one point, which isn't really possible according to the definition of a gradient, we'd instead draw a line and find the gradient using 2 points on that line. So let's start doing that, and we'll consider this point over here, which I'll call P, with coordinates 1, 1. Now the next step that we said is to draw a line at this point. But now you might realize that there's quite a lot of lines that you could draw at this point, and it seems like they all have different gradients. So how about first let's try looking at this point and the line between them. And I'll call this Q, and it's got coordinates 3, 9. So now using the formula for the gradient of a straight line, we'll work out the gradient of this line PQ. So we know this is equal to the change in y over the change in x, which is 9 minus 1 over 3 minus 1, which comes to 8 over 2, which is 4. But how are we certain that this line gives the gradient at this point? Well, we can maybe try another line. We'll try the line between P and this point over here, which I'll call Q dash with coordinates 2, 4. So now repeating the same process, we'll find the difference in the y, which is 4 minus 1, over the difference in the x, which is 2 minus 1. And this gives you 3, which appears to be more accurate, since our second line seems to be closer to the curve than the first. So now let's consider a third point and the line between it, which is as close to this curve as we can get on this scale. And I'm going to call this point Q dash dash with coordinates 1.001 and 1.001. Now, of course, this may not be totally accurate or to scale, but I think it'll work well. So now, choosing a third and even more accurate point, I'm going to call this Q dash dash with coordinates 1.001 and 1.001 squared. Remember that because this function is f of x equals x squared, the y coordinate is always going to be the square of the x coordinate. And this is true for all functions on this curve. So now in the same way as before, we'll work out the gradient of this new line, pq dash dash. So now working all of this out, you get a final answer of 2.001. Notice that the point Q, which has the largest difference from P, and the line that we drew from it, is less accurate, and we know this because the line is furthest from the curve. But when we move this point closer to P, we get a more accurate line, and when we move it even closer to P, we get an even more accurate line. And you can imagine this as our point on the curve getting closer. So now as our point gets closer and closer to P, the line gets more and more accurate. And this continues until we get the most accurate line is the line which touches P at only one point before moving away from it. This is known as the tangent at P. Therefore, to find the most accurate gradient, we want to find the tangent at P. However, remember that the gradient has to be between 2 points. But as we can see with our final point, even on a line which appears straight and appears to be a tangent, there's always 2 separate points which have a really small difference, such as 0.001 for us. So to recap, we find that as the x distance between our 2 points decreases, the tangent gets more and more accurate. Here the distance between our x values was 3 minus 1, which is 2. Here the distance was 1, and here the distance was 0.001. So the closer our point is to P, the more accurate the gradient. So now let's try and find the tangent to the curve using algebraic notation, following the exact same process that we did over here, but with algebra instead. This red line is the tangent to the curve at P, and this is what we're going to be trying to reach. But let's consider any point. We'll call this R. So now instead of using an exact value for P, where we used 1 and 1 before, we'll say that P is equal to x and x squared. Remember that this function is of f of x equals x squared. So this means that the y value is always the square of the x value. So if we let this x value be equal to x, then this y value would be x squared. We'll call the x difference between P and R, which should be around this, h. P's x value is x. The difference between P and R is h. This means that the x value of R is equal to x plus h. Because our function is f of x equals x squared, the y value for R has to be x plus h squared. Now we can use the same definition for the gradient to find the gradient of PR. The change in y divided by the change in x. So to find the change in y, we would be looking at x plus h squared, which is our second y value, minus our first y value, which is x squared. And this would be all over the change in x, which is x plus h minus x. Now when you expand the brackets on the top, you're left with x squared plus 2xh plus h squared minus x squared all over. The x and the x cancel here, so we're left with all over h. Now we can see that h is a common factor in both of the terms at the top. So we can cancel h from the top to leave h over there, and cancel h to leave 2x over there. So this leaves us with 2x plus h as the gradient for PR. But remember, to find the most accurate gradient at P, we want to find the tangent to P. So right now, our hypothetical PR looks like this, but we wanted to get as close to this tangent line as possible. Like we talked about before, we want to make the distance between P and R smaller as it moves down the curve. To do this, we have to make h as small as possible. Referring back to our first diagram, h was equal to 2 with PQ, 1 with PQ dash, and then 0.001 with PQ dash dash, which had the most accurate result. So as h decreases and r gets closer to P, the line PR moves over closer and closer to the tangent line which we want. This means we want h to get infinitely smaller to get the best tangent line, meaning we want it to be approaching 0. So as h approaches 0, the gradient is then equal to 2x. Because as h approaches 0, we can cancel it out, leaving 2x as the final answer for the gradient. We can make our points that we use, P and R, even more general by writing P as x and the y value f of x. But the y value is always going to be the value of x put into that function. Similarly, R is always going to be x plus h for some distance h, and then f of x plus h. Note that sometimes you may see h written as delta x. Working out the gradient for PR, we work out the gradient function. What this means is that when we plug in an x value into this function, our output will be the gradient at that point. So earlier we were looking at x equals 1. When you plug x equals 1 into our gradient function, you get that the gradient is equal to 2. And looking at our 3 examples, we can see that the gradient is approaching 2 the nearer you get to p. More formally, we can write the rule for finding the gradient function as the limit as h approaches 0 of f of x plus h minus f of x all over h. You can see that this is the difference in y's at the top, because y is going to be f of x plus h and f of x, and the change in x at the bottom, because the change in x is always going to be h. Because we want h to be as small as possible to get nearest to the tangent line, we want h to approach 0 at the end once we've dealt with all of the algebra. You might also more commonly see this written as dy over dx equals f of x plus h minus f of x all over h. The dy over dx encompasses the limit as h approaches 0 already, so there's no need to write that as well. And this form of differentiation, using the rule for the gradients, is known as differentiating from first principles. So we've already seen how this works when f of x is equal to x squared, so now let's try it for f of x is equal to x cubed. So looking back at the general formula, we plug x plus h into the function. So here the function is x cubed, so we write x plus h cubed minus f of x, which is x cubed, all over h. After expanding the brackets, you're left with this numerator, all over h. Similarly to last time, the first x cubed cancels out, and the h cancels out with h in the numerator. So you're left with the limit as h approaches 0 of 3x squared plus 3xh. Now applying the limit when h approaches 0, you have 3 times x times 0, which cancels this part of the expression out, leaving you with 3x squared. Similarly, when using our general rule for the function f of x is equal to x to the 4th power, you're left with 4x cubed as your answer for the gradient function. Now at this point you might start seeing a pattern emerging for all of these functions that we're covering, and this is known as the power rule. Now although this might seem slightly complicated, all that the power rule tells us is that when you differentiate a function of the form kx to the n, this includes x to the 4th power, where we have k is equal to 1 and n is equal to 4. You multiply the power to the front, and then subtract 1 off the power, to leave you with the function in the form kn(x to the n minus 1th power. Now looking at a few examples, we've got dy over dx of x to the 5. Bringing the power to the front, we have 5, and subtracting 1 off the power, we have x to the 4. For a function with something other than 1 as your k value, we can consider something like 2x cubed. So here you bring the power to the front, so you're left with 3 times 2, and you take 1 off the old power to have x raised to the power of 2. And this is equal to 6x to the power of 2. Finally, looking at a function such as 1/4 x to the 4th power, multiplying the power by the front, we have 1/4 times 4, which is just 1. And subtracting 1 off the old power, we have x cubed, and this is equal to just x cubed. We can apply the power rule multiple times in a function if needed. So here first we start off with the 3x cubed term, and we apply the power rule to bring the 3 to the front and take 1 off the original power to get 9x squared. Do the same thing for the x squared term to get 4x, and finally the same with the 2x term to get a plus 2. Notice that when applying the power rule here, x is really just x to the power of 1. So we bring the 1 to the front, multiply by the 2 to get a 2, and then take 1 off the original power to get x to the 0. However, x to the 0 is just equal to 1, That's why we get 2 times 1, which just leaves us with 2. Similarly, looking at the constant term, this can be written as 4x to the 0, keeping in mind that x to the 0 is equal to 1. Then when multiplying this power back to the front, you're left with 0 times 4 x to the minus 1. However, 0 times 4 is 0, so this cancels out this whole term. From this, we can gather that when differentiating, if we have any constant terms, like 4, we can just completely ignore them in our derivative function. After differentiating to find a gradient function, in this case 2x, we can see how this can be used to find the gradient at separate points. This is the graph of f of x is equal to 2x, and we can see that at x equals 1, the gradient is equal to 2. Remember that originally, working out the gradient at p, we found that the gradient approaches 2. When you plug an x value, for example x equals 1, into the gradient function, you receive the gradient at that point. So let's say we wanted to find the gradient of f of x is equal to x squared at, we'll say x is equal to 4. So after differentiating, we find that f dash of x, or dy dx, is equal to 2x. And substituting x is equal to 4 into the gradient function, we find that the gradient is equal to 8. One of the things which confuses people the most during differentiation, so we'll quickly go over that just to clarify what is going to be used when. So to start off with, f of x is the function that you're asked to differentiate. This might be in y equals form as well. Here, f of x is equal to x squared. A lowercase delta x, or the letter h, is used to signify a small change in x, as can be seen over here. And this small change in x is usually put into a limit when differentiating from first principles like we've done over here. This makes the small change in x approach 0 so that we get as close to the tangent line as possible. The derivative function is the function we obtain after differentiation. So here the derivative function is 2x. And the most common notation you see for the derivative function is either dy over dx or this which is called f prime of x or f dash of x. But what makes this notation different is that it's only used after the limit of h approaching 0 has already been applied. So for example, the gradient function 2x plus h could be written as dy over dx, but with lowercase deltas. However, the final derivative of a function, which is 2x, which is found after h is made to approach 0, is written as dy over dx. This is probably one of the highest level question types that you'll see concerning differentiation at GCSE level maths. We're asked to find the tangent to the curve, f of x here, at the point 2 minus 8. And to solve this problem, we need to use a culmination of multiple different rules that we know already, including some more basic algebra, the power rule, and finding the equation of a straight line. So firstly, we want to write f of x into a form which we can differentiate using the power rule. And we can do this by expanding these brackets. So expanding these brackets, we have f of x is equal to x squared minus 4x plus 2x minus 8. And tidying this up, we have x squared minus 2x minus 8. Now to differentiate and find the derivative function f dash of x, we apply the power rule to each of the terms. So we're left with 2x minus 2. And now you must recall one of the ways which we can write the equation of a straight line. Y minus y1 is equal to m times x minus x1. Note that here, x1 and y1 denote the single point that we're given in the question to work with. We don't need to find y or x, since these will form part of the equation which we'll have in the form y equals mx plus c. And we already have x1 and y1, which is 2 and minus 8. But the only thing which we don't have and which we need is m, which represents the gradient at this point. Once we have a function, we can use the derivative of its function to plug in the x value and find the gradient at that point. We have the derivative function at 2 is equal to 2 times 2, because x is equal to 2 here, minus 2, which is equal to 4 minus 2, which is just equal to 2. So now we have enough information to put this into the formula for the equation of a straight line. So we have y minus 8 is equal to m, which is 2, times x minus x1, which is 2. These two negatives cancel out, so we have y plus 8 is equal to 2x minus 4, and then subtracting 8 on both sides, we have y is equal to 2x minus 12. So to recap, first we found the derivative function, we found the gradient at the point where x is equal to 2, and then we simply substituted this in to the equation of a straight line to get the equation of this tangent. Alternatively, you could use the y equals mx plus c form after finding the gradient. So here we would have y is equal to 2x plus c, and then to find this missing value c, you substitute our value for x and y. So you have minus 8 is equal to 4 plus c, because 4 is 2 times 2. To find c is equal to minus 12. And then putting y and c into the equation of a straight line, we have y is equal to 2x minus 12, which gives you the same result. And you can see that when graphing the equation f of x, at the point 2 minus 8, the equation of this tangent is 2x minus 12, which is what we found using differentiation. The final significant part of differentiation for GCSE involves finding stationary points, which are also known as maxima and minima of functions. Another more common name for these is the turning points. And this describes exactly what they are, the points at which the function turns. So for example, we can see that this is one turning point and this is the other turning point. That we can quite easily see the coordinates of these turning points. But suppose we wanted to find these turning points without having graphed the function and only using the equation. This is also something that we can do using differentiation. Notice that at these turning points, the gradient is equal to 0. So if we wanted to find the gradient at this random point over here, we can see the gradient is clearly positive. And at this random point over here, the gradient will clearly be negative. However, at this turning point, the tangent to the curve is a straight line, which means that it has no gradient. In other words, the gradient is equal to 0. Similarly, the tangent to this curve at the turning point over here is also a straight line, meaning the gradient is also equal to 0. Remember that we use dy over dx to signify the gradient function or the derivative. And using the tangents of this function, we can see that at the turning points, dy over dx has to equal 0. So in this case, f of x is equal to x cubed plus 3x squared minus 3. This means that dy over dx, or f dash of x, remember that they're the same thing, is equal to, now using the power rule, 3x squared plus 6x. Now remember, at the turning points, dy over dx is equal to 0. So this means to find the coordinates of the turning points, we can set this derivative function equal to 0. So this means 3x squared plus 6x is equal to 0. And now we can solve this like you'd solve any other quadratic. Factorizing out x to get 3x plus 6 equals 0. So this means either x is equal to 0 or 3x plus 6 is equal to 0, which would mean x is equal to minus 2. And now we can see, looking back at our graph, that at x equals 0, we have a turning point, and at x equals minus 2, we also have a turning point. So this makes complete sense. But now, again, suppose that we didn't have this graph, but we wanted to find the y values that go with these x values. Well, to do that, we simply have to plug these back into our original function. So this would mean at x equals 0, the y value would be f of 0, and plugging 0 into this function gives you minus 3. And similarly, we input x equal to minus 2 into our function to get minus 2 cubed plus 3 times minus 2 squared minus 3, and this is equal to 1. Using only differentiation and algebra, we found the stationary points to be 0, minus 3, and minus 2, 1. A similar example question which we could get, without the use of any graph, is to find the maxima and minima of f of x is equal to x cubed minus 3x squared plus 6. Now we follow the same process. First, we differentiate this function to get that f dash of x is equal to 3x squared minus 6x. Recall that at the turning points, f dash of x equals 0. So we have that 3x squared minus 6x equals 0. And factorizing, we have 3x, x minus 2 is equal to 0. This means that either 3x is equal to 0 or x minus 2 is equal to 0, which means that either x is equal to 0 or x is equal to 2. Now to find the y values of the points which go with these x values, we have to simply plug them back into the function again. So we do f of 0 is equal to 0 cubed minus 3 times 0 squared plus 6, which is just 6. And then f of 2 is equal to 2 cubed minus 3 times 2 squared plus 6, which is simply equal to 2. So this means our two stationary points are 0, 6, and 2, 2. But we have to clearly list which one is the maxima and which one is the minima. We know that these 2 points are both stationary points, but how do we know which is which? So the best option here, something which we can do, is to sketch a very quick and very rough graph of the function, which will give us a better idea of how it will look like and where each point will be located on. So first we know that 0, 6 would be around here, and then we can say that 2, 2 is somewhere around here. Because this function has a positive x cubed term, we know that the graph will be going from left to right. So it should look something, again, very rough, like this. We can clearly see here that 0, 6 is the maxima because it's the higher turning point, while 2, 2 is the minima because it's the lower turning point. We can clearly see here that 0, 6 is the maximum point because it's the higher turning point, while 2, 2 is the minimum because it's the lower turning point. So this means that the maximum point, so this would be our final answer. And finally, looking at the graph of f of x, we can see that our maximum and minimum point were correct, and also the sketch was kind of accurate. So it did the job in helping us tell which one was which. Now you might just think, well, 6 is higher than 2, so surely 6 must be the maximum and 2 must be the minimum, right? However, this isn't always the case. You can get some strangely shaped functions which don't always work in the same way, so it's always worth sketching the graph to get a rough idea of how it looks like if you know how to draw it. This video covered everything you need to know about differentiation for the GCSE Maths course. Please remember to like and share this video, subscribe to the Ali Khan Math YouTube channel, and leave a comment with any feedback or any requests for topics or questions. Thank you so much for watching.